Okay, so good morning, and my name is Tiantian Gong. Actually, just go by Tian. I'm currently a postdoc working with Professor Fan Zhang in our department and Professor Yao at Technion. So today I will be talking about how to invite you to investigate the curious case of relaxed behavioral assumptions in secure distributed computation. So in secure distributed computation, there is like such as like secure sharing schemes, secure multiple computations, or MPC for short, or multi-server private information retrieval, or PIR for short, or consensus protocols. They are typically behavioral assumptions on the participants. So depending on the security level we're trying to achieve, whether information theoretical or computational and the adversary model in the system, we will typically be able to tolerate some upper bound on the number of faults that we can tolerate. In other words, there will be a lower bound on the number of honest parties we need in the system. So the question we're interested in is that what if your party is actually honest? So because honesty is not some commodity for sale, so what if we have either more rational parties or more malicious parties? So we will be investigating this from 3 angles, but we will mostly be focusing on the first 2 angles, and the third angle we will be catching or discussing it only if we have time by the end, but I will focus on the first two due to time constraints. So the first one is on rational parties attacking privacy outside of secure multi-party computation protocols. And this will be based on joint works with Professor Somas, Professor Henry, Hai, Professor March, and Professor Kate. The second angle will be on fair reconstruction. In secret sharing, when we have rational participants only. This will be based on joint work with Zoe. And we will start with the first angle, of course, and to characterize how people will be able to attack privacy, we will need to first characterize who can break it. And this is precisely what access structure will be capturing. So an access structure is a collection of subsets of parties who will be able to reconstruct the secret. We will be interested in monotone access structures only. So if the group of party can reconstruct, then their superset can also reconstruct. And we will be also interested in another notion called minimal access structure. This will retain only the minimal groups in the access structure. So for example, if we consider T threshold secret sharing or T-1 private PIR, then the access structure will be retaining all the groups with size greater or equal to T. So the minimal access structure here would be retaining only the groups with size exactly T. So for additive secret sharing, we have a singleton access structure containing only the party set. And for a asymptotic example, we have included another access structure. We have two minimal sets, and the supersets for these two minimal sets will also be in the access structure. So this will be about who can break privacy. And then we will be briefly introducing two primitives that we will be focusing on today. The first one is verifiable secret sharing. So VSS is simply a secret sharing scheme with verifiable shares. So a secret sharing scheme would allow a party to a dealer to share a secret among group participants according to certain access structure. And take the prior toy example access structure as an example. So initially, the dealer will be holding a secret, and every party will be waiting for a share. So as a first step, the dealer will generate shares from a share generation algorithm and send the shares to the parties. The parties later will be able to reconstruct from their shares if they are indeed in the access structure. So the security of secret sharing itself contains correctness, where groups in A will be able to reconstruct, and privacy, where groups not in A will not be able to learn extra information about the secret from their received shares. The other primitive we're interested in will be private information retrieval. So we will parameterize it with two parameters K and T. And it means K out of K, T private PIR. So we'll also be using a database in the algorithms for PIR. And typically the workflow is as follows. The client holds an index of interest. She wants to query the entry of this index in the database D. And the servers will be holding this database D. So the first algorithm is for the client to generate the query strings from the index. send the query strings to the servers. Then the servers will be computing the answer strings from the queries, send the answer strings to the client. And finally, the client will be reconstructing using the answer strings. The security of the PIR scheme would include also correctness, where the client should be able to reconstruct the entry dx star if it receives k correct responses, and privacy, where the less than t+1 parties will not be able to learn extra information about the index from their received query strings. So these are the two parameters we're interested in, and the problem we're interested in is the privacy targeted collusion. So in PIR, it would specifically require the parties should not be able to collude, reconstruct the index. But in secret sharing, it's more nuanced. So the standard security definition for secret sharing does not concern who can, it only concerns who can reconstruct and who cannot, but it does not concern when. So in some applications, the parties are not supposed to be reconstructing. So for example, in multi-device cryptocurrency wallets and distributed key generation, the parties are not supposed to be reconstructing the secret signing key or the secret key. And but in some other applications, they can reconstruct, but they can only reconstruct after certain conditions have been met. So for example, like in secure multi-party computation, the parties are not supposed to be reconstructing the inputs, but they are supposed to be reconstructing the final output. Okay, so what we wanted to deter or mitigate is the privacy targeted collusion when the parties are colluding to reconstruct some secret either prematurely or illegally. So because we're considering no honest party situation, so our goal can only be designing some mechanisms to disincentivize rational parties from participating in collusion, while tolerating some malicious parties because we can't control malicious parties in any way. So this idea is not completely new of using rationality to disincentivize parties from collusion. So in traceable secret sharing, the colluding parties are assumed to be colluding using a specific way. So they construct some stateless reconstruction box for other people to query. So there exists a tracer who would be able to make queries to the reconstruction box, and from the responses, they will be able to know who created this reconstruction box. So in this way, they can locate some of the colluding parties. Of course, this is a very specific way of collusion. And in secret sharing extinction, they took it one step further. So they assume the parties will be colluding using MPC instead of putting out some visible reconstruction box. So by assuming that computing a large number of hashes on a distributed secret with MPC is going to be hard or taking significantly more time than computing this many hashes on the secret itself, then there is a gap that we can utilize to protect the secret. But the secret is not protected beyond that point. So what we did in our collusion deterrence mechanism is to allow collusion to happen in any way. So the parties can use unobserved communication channels and any arbitrary methods. So our goal is only to disincentivize successful collusion where the parties have learned something non-trivial about the secret. So if they haven't learned anything useful, then we do not care about it. They can collude whatever you wanted. So the mechanism here is simply a set of rules, or two rules specifically. So here the allocation rule will be labeling people. The payment rule will be deciding the payments based on the levels of people. So essentially, it's going to be a public algorithm on a public bulletin board that parties can interact with. So that's the mechanism. It's just a bunch of rules that are public, and it will affect parties' decisions and actions. We wanted to design the mechanism in such a way that we reach some desired outcome. So our model, in summary, would be as follows. We consider a mix of rational and malicious parties. Rational parties try to maximize their utility. Malicious parties behave arbitrarily, and when we consider malicious corruptions, we consider it adaptive. And for rational parties, we only consider individual parties in this talk, but we do consider strong coalitions from a cooperative game theory perspective in the papers. So the second one is for the collusion method. As we mentioned, we don't assume anything about how parties collude. And for Additionally, we also capture set information. So the parties can already have a pre-existing knowledge about the secret. So what this implies is that we will need to distinguish between learning some secret through pre-existing knowledge and through collusion somehow. And finally, our goal is to deter successful collusion under general access structures. So we will start with a singleton access structure. So in this case, when we detect collusion, we know immediately who colluded, because everybody should have colluded. So our task is only to detect collusion in some way. And let's do a thought experiment. Suppose we are trying to protect some unknown secret f x star. So x star is the actual secret and f is some non-trivial information about it. So we just call this whole thing a secret. And what is known to us is an upper bound on the worst of the secret, and we have a set of parties. So for the thought experiment, we just have a very simple scheme. We will select the party P1 if party P1 tells us the correct secret. And everybody else will be marked as colluders. So in the payment rule, we just reward the winner and penalize every marked colluder. So we, of course, will penalize this party P1 if it tells the wrong secret to in an attempt to do a fake accusation. So let's do a simple analysis with everybody being rational. So of course, P1 is going to be incentivized to second the collusion after successful collusion, and other people are not going to be incentivized to let P1 learn the secret because of this large penalty. However, so there are many unsolved questions or unanswered questions here in this simple scheme. So first one is that how can P1 tell if collusion has been successful? Because they may only receive output, and what if the output is actually wrong? It's not something about the secret. And second, nothing here is stopping P1 from helping other people learn the secret. And third, P1 can have arbitrary prior knowledge about secrets so that they can potentially frame other people. And fourth, how do we verify the report of the secret, given that the mechanism is actually some public algorithm at some public place? So, and finally, how should we set up the payment rules so that we achieve the non-collusion outcome, which is what we desire? So about the first question, it depends on whether they have input verification gadgets in the collusion protocol. If they do, then they can directly tell. Then it depends on whether the portion the inputs is going to be computationally hard or not. So if it's computationally hard, then we call this verified collusion. So the party can just verify whether the output is gibberish or not to know whether other party has forged inputs. But if it is not computationally hard to forge inputs, then we call this blind collusion. And in this case, you cannot judge from the output of the collusion protocol to see whether other people have behaved in collusion. So we will focus on the verified version of the collusion protocol, but the blind collusion requires a different technique to analyze it, but it's actually easier to mitigate because they are already making their life hard to allow each other to cheat in collusion. And next about how to stop P1 from helping other people learn. So this is actually simple. We can just democratize the winner selection rule. Anybody can become the winner if they provide the correct secret. So now with this change, we don't need the reward amount to be positive anymore because the parties are going to be reporting not because they wanted the reward, but because they wanted to escape the penalty. Since we're only rewarding the first correct secret teller, so all the parties, if they don't have a network advantage over other people to support the report first, then they won't be discouraged from collusion. Does that make sense? Okay. Yeah. So next, about accommodating arbitrary prior knowledge about the secret, we will be generating like random companion queries. So take PIR as an example. So suppose you initially the client wanted to query index X star, then we can sample some random index XR, and the client can generate query strings for both of those indices and generate a random computation to commute those two query strings. And then the client can send the commuted query strings to the parties. The party can send back the answer strings, and the client only need to reconstruct the corresponding answer strings to get the intended queried entry. So we are using randomness to accommodate prior knowledge about the secret. And finally, non-finally, next about how do we verify the reports. we will need to change the protocol a little bit and also still take an PR as an example. So initially the client will need to commit to all the query strings and send it to the bulletin board to the mechanism. So the mechanism now knows the commitments of all the query strings. And then the client will be sending the commit information to all the parties or the corresponding parties. And then the parties will be computing the responses and they will be committing to the responses as well and send the responses to the mechanism on the bulletin board. And finally, the parties or the servers will be sending the responses or decommitting information for the responses to the client. The client can do the final reconstruction step. And then when we have a collusion report, everybody just opens up their commitments and the mechanism will perform computation on the plain text to verify whether the submitted report is correct or not. So this is a very dumb method because it is not dumb, it works if we have 0 malicious parties. So if the mechanism achieves the non-collusion outcome in equilibrium and nobody submits false reports, then this mechanism is actually never called. So nobody submits reports at any time. So the commitment revealing is never happening. So we are preserving the secret. But later we'll be discussing how do we handle malicious parties' existence, because malicious parties will be submitting fake reports to force commit revealing, and that's not desirable. Okay, so finally, we will be talking about how to parameterize the payment so that we have the desired outcome. I will try to explain this in an intuitive way without involving the solution concepts and how do we solve for equilibrium. And we needed to essentially parameterize the reward, the penalty, and the service fee here. We're charging the service fee only to motivate the parties to participate and disincentivize the client or whoever is stealing the secret from colluding with other people. Okay, so to characterize the desired outcome, we have to first characterize what people can do. So the parties can, after they receive some secret, either it's a share or a string, so they can decide whether to collude with other people. And then they can decide whether to input correct information. And finally, they decide whether to report. Our desired outcome is then the party is either going to be playing not colluding in the first stage, or they play colluding but input incorrect information in the second stage. So if we're running this mechanism or this entire system only once, and we're considering only rational parties, then it's very simple. We just set this penalty to be sufficiently large so that if you're one of the K parties who are colluding, if you cannot beat all the K-1 parties in terms of the race to report collusion, then you don't want to collude. So by the rule of means, there is always somebody who is not faster than everybody else. So this party is disincentivized from collusion because of this inequality we are having here. So as we noted before, we don't need the reward to be positive because people are going to report not because they wanted rewards, but because they wanted to escape the penalty. And we also have some conditions on the service fee so that we can discourage client collusion. But this is all the main parts we're discussing here, so we will just briefly mention it. And as you noticed, there are 2 tags on the theorem 1. So what if we're running this for like repeated times? So if we're running this for a known finite number of times, then we can still achieve the same outcome with under the same condition. So this is because we are solving for our equilibrium with backward induction. So as long as we have a place where we can start our backward induction, this still applies. But if we have infinite or unknown number of runs, this ceases to work because we don't have a final point, final game that we can start reasoning about. So this has been proven in folk theorem and also in well-studied games and in real-world examples. So the intuition would be, I can play, if I am a colluding party, I can play a grim trigger strategy. I can tell all the other rational parties that if you collude with me and you report me, I will never collude with you again, so you will never learn another secret. So because of this kind of threat, they would be cooperating over and over again just to learn every single secret. So how do we handle this? The first one is to have way more parties in the system than you need. So every time the client will be picking k parties out of some large number of n parties to do the computation with. So if we don't see each other very often, then my threat to you, the golden trigger strategy, it's not credible to you or doesn't make you change your mind. So if you want, especially if the reward is non-zero now. So that's why in the first condition, we have the reward to be some at least some amount. So if the reward is large enough, then you don't feel bad about betraying me, because if we just see each other once a time or once in a year, then you don't feel bad or you don't lose utility if you betray me. So that's intuition there. And we have a small figure on the right-hand side to show that with n increases, the condition, the lower bound on the reward amount is going to be expanding. And as a result, other parameters can be set within a larger parameter feasibility region as well. But if you do not want to have a lot of parties in the system, you can also take the alternative where you just tell everybody they are going to be in service only for a finite number of times. So at the beginning of every year, you just have a new set of players in the system. This will also reduce this infinite repetition to finite repetition. And we have the exact same outcome under the exact same condition in SEM 1. And we also prove that practical parameters always exist. And this is only to show that we're not living in imagination land. So next we will be adding malicious parties. And it first changes the parameterization, and then it changes the report verification process. So for the parameterization part, we are now just, if we consider adaptive corruption, so then we can only tolerate up to k-2 adaptive parties. And the two remaining parties will be playing this collusion game, and we will be parameterizing all the penalties or all the payments in the system by considering only two parties playing the game. Similarly, if we consider static corruptions, we can do the same computation for the game played by two parties. And the next about our report verification mechanism. So initially we had this commitment revealing scheme. It will not be working or protecting the secrets in this case, because malicious parties can submit fake reports. Even if they get punished, whatever, they don't care. They learn the secret by paying some money. So we will be changing this to a two-step verification. In the first step, some party is going to submit a report which consists of three parts. It reveals the commitments where the plaintext was used to generate some knowledge about certain secret acts. And second, you will be telling this non-trivial knowledge about this secret acts. It could be the most significant bit or least significant bit or like half of the bits. And the third content is a description of the function. So using this information, the other parties are supposed to be producing some proof by the deadline. And the proof is going to be some inequality proof. These parties need to show that either the function is trivial or prove that their inputs are correct with respect to commitments, and the function f is being computed, the output is not the value in the report. So they can use collaborative zk-SNARKs protocol if k is greater than 2, but if k equals to 2, then we can just use normal zk protocols to perform this task. So in this way, the adversary will be able to test whether their guesses are correct, but they will not be able to learn the secret directly. Does this make sense?
What is the value
You mean value V?
and the previous in the previous?
Yes, so V is the upper bound on the worst of the secret. The upper bound on the secret worth. So the secret could be worth $100 at most, so V equals 100. Yeah. Yes, so this will be how we verify reports in a privacy preserving way.
This seems expensive.
Yes, this is expensive, and the malicious party are supposed to be paying for it. So if this report P3 is submitting turns out to be a fake, a bogus report, then P3 is going to pay for everything. Yeah. So the final mechanism would look like this. We have a winner selection rule where if any party tells the correct secret first, along with its input and the proof for inequality is now provided by certain deadline, then this PI is selected as the winner and everybody else will mark it as colluders. So, and the payment amounts will be set according to the theorems we had before. And so far we have a way to disincentivize a singleton from collusion. And we have talked about the individual rational party case. And if you are interested in like more like strong collisions or some other specific details, we can discuss later, or you can refer to the paper. And the next step will be about general access structures. So the change will be now the detection of collusion doesn't necessarily tell us who colluded. Right, so our main task will be to locate colluding parties. So we can start with our prior mechanism and with a very small change. So if any party tells us the correct secret first, and we will be selecting this party as winner, and all other parties will be marked as colluders, even if they are not in the same access group. So even if they didn't collude with this PI, everybody else will be penalized. So this type of blanket penalty is not credible in the sense that some parties might prefer other people to be penalized. So if I am evil, so I will feel devastated if I am the only one who is penalized, but I will feel very good if everybody else is down with me. So in this case, this party would be able to externalize the harm onto other people. So penalty here is no longer a penalty, a negative thing. It can be positive. So so this kind of mechanism will cease to be effective. We will capture this with a notion called fairness hazard. So it measures the maximum number of non-colluding parties being penalized by the mechanism if we have K-1 malicious parties. So here K-1 is the maximum number of malicious parties that we aim to tolerate, because if K parties are malicious, then we can do nothing about it. So the fairness hazard of this mechanism W0P is going to be minus K. So in the worst case, everybody else in the system who are not colluding are penalized. So the natural question is, how do we do better than this? How can we reduce this fairness hazard? And to do this, we will be needing to introduce some structure to the access structure itself. And recall that the access structure we're considering is monotone. And additionally, for simpler representation, we'll also consider K-homogeneous access structures. So all the minimal sets will have size K. So here A0 will be a 3 homogeneous access structure. And the next property we will be introducing and caring about is robustness, which is the minimum number of parties whose absence would make reconstruction impossible. So why do we care about this? Because if we didn't care about robustness at all, then we can always use the singleton access structure. So why do we go for general at all, right? And the final notion is called trackability. This is how we add structure to access structures. So an access structure is omega trackable if any set of omega parties is contained in at most one minimal set. And now we can parameterize the trackable access structure or TAS with 3 parameters and K omega. So it just means a K homogeneous omega trackable access structure and parties. So for example, A0 will be a 6, 3, 1 trackable access structure. So we will later be using this, but first let's make an attempt if we would say if what.
Okay. So over the TAS with the signal.
Yes.
One.
So for A0, we have two minimal sets, 1, 2, 3, 4, 5, 6, and it also contains order supersets. So, but we only care about the minimal sets. So if we are given party 1, we know it's the first minimal set. If we are given party 5, we know it's the second minimal set. So in this case, the access structure is one trackable. So as long as we're given one party, we know we can pinpoint at most one minimal set. So if there is another party, say 7 in the party set, but it's not including any, say, any of the access group, then the 7 will not be included in any of the minimal set. So this will still satisfy our definition. So we only require that any of the omega parties will be able to let us pinpoint as at most a single minimal group.
So why is it not two trackable?
It is also two trackable. So one trackable is yes. So it's going to be the one trackable is stronger than two trackable. So one implies two trackable and implies three trackable up to K, the homogeneity parameter.
The additional threshold parameters that you might respond trackable.
So for yes. So for threshold, yes, good point. So for threshold access structures, it's actually not trackable. So even given K minus one party, the other party can be anyone. So you can only pinpoint a unique group if you are given exactly K parties. Yes, so we will mention this probably by the end, but for untrackable access structures, this mechanism we are developing next will not be useful because this threshold access structure is not trackable. Yeah. Okay, so we will be using tasks later, but for now let's make an attempt to see what we can do without any structure to the access structure itself. So we have a simplified mechanism here, but if we want it to be comprehensive, we would write out something as earlier. So here in mechanism 1, we would reward the first correct reporter and penalize everybody else who are in the same minimal set with this reporter. So now we definitely have, not definitely, we could potentially have smaller fairness hazard. So consider this access structure we had before. 1, 2, 3 are in one group and 4, 5, 6 are in another. Suppose, except for 2, all the other parties wanted to collude, then 4, 5, 6 can potentially successfully collude. So if without loss of generality, suppose 5 has the fastest network connection, then 4 and 6 will be disincentivized from collusion because they are going to be penalized by their coexistence with 5. So this is going to be fair because only in this access structure, because we're not penalizing anybody who is not in the access group with 4, 5, 6. However, this will not work if we have say a different access structure. So suppose we have 3 minimal groups here, 1, 2, 3, 1, 4, 5, and 2, 4, 6. So now if everybody except for 2 wants to collude, and 1, 4, 5 might succeed. And in this case, suppose 1, unfortunately, is the fastest one. Then when we are given up to 1 malicious party, 1, 4, 5 does include, because there are at least 2 rational parties in each group, then the 2 rational parties will be having the race condition, will be racing to report, and they don't want to cooperate with each other. But if we are given actually 2 malicious parties, say unfortunately 2 and 4 and 5, then 1 will be able to collude with 4 and 5 and report first. And then in this case, 2 and 3 will be penalized. In the worst case, both of them might be non-colluding. So the fairness hazard is going to be 2. So let's make a second attempt to use our trackability. So we can observe that A0 star is actually one trackable. So we can just reward the first omega correct parties, correct reporters, and then penalize everybody else in the same minimal sets with these reporters. So in A0 star, we can achieve 0 fairness hazard even if we're given 2 malicious parties. because here, suppose 4, 5, 6 collude and 4 reported, 5 and 6 are malicious, then the malicious parties are the only one penalized. So, but however, of course, this is not going to be sufficient. Let's consider like a slightly more complicated access structure. So here A2 star has 7 minimal groups. So each line, including the circle in the middle, or Byzantine access group. So this is going to be trackable because any 2 points will pinpoint a unique line or a circle. So in this case, what if we have everybody including except for 2? So if 1 and 3 are actually the fastest to report, then 2 is going to be penalized. And even given 0 malicious parties here, we are not achieving the non-collusion outcome, and the only non-colluding party is penalized. So it's not effective, it's not fair at all. So why is this happening? It's because we are having multiple groups colluding at around the same time, reporting around the same time. So the first omega reports actually come from different groups. So how do we handle this? We will have to do some, so this would indicate that trackability alone doesn't actually guarantee the precise assigning of blames in cases of collusion. So we will need to do some noisy signal sanitization. So if we are having exactly omega reporters, we can uniquely identify, if we can uniquely identify a minimal set, then we reward these reporters and penalize everybody else who is remaining in that minimal set. And the sanitization will happen in the first step. If we have more than omega reporters, then we will first penalize the last free rider who doesn't complete a minimal set within other reporters. So if a free rider doesn't exist, then we penalize the last reporter. So in the first step, we don't penalize outside of the reporters. And finally, if in any other cases, if we have like less than omega reporters, then we distinguish the reports. So how, like intuitively, how this will work? Suppose we have this, we're faced with the same situation, and suppose this is the network speed of the 6 colluding parties. We can consider any other sequences as well, but this is just to show the intuition by the end. So here, if 7 says that 1, 3, 4, 5, 6 have reported collusion, 7 does not want to report because of this last reporter penalty. Considering that 7 will not be reporting, 6 will also not report because of this last reporter penalty. Considering 6 and 7 are not going to be reporting, then 3 doesn't want to report due to the free rider penalty. And then next for 5, no matter what it does, it's going to be penalized either as the last reporter or as the remaining party in a located minimal group. So the intuition here is that the slowest parties in the fastest group are going to be disincentivized from collusion. And then reasoning backwards, the slowest parties in the second fastest group are also going to be disincentivized from collusion. And this will go back to, we can just reason backwards to every single group. So slow here, we're using it in as a opposition of fast. So as long as you are not faster than other people, you are slow. So you could be having the same speed, but as long as you are not faster, then you're slow. So this final attempt is effective, and we can show it more rigorously, but I think this visual proof tells us some already conveys the intuition behind the effectiveness of this attempt. So finally, let's compare the two. Yeah, please. They will have to know whether they're faster than their group.
Just the group.
Yes. Yes, so we are assuming here the party would know whether they are not faster than other people in their group. And because of the rule of means, so there always exists this party. So we just reasoned that this party would be discouraged from collusion, then collusion wouldn't successfully happen because you don't have enough shares or queries to reconstruct the secret from. Yeah.
Do you need that assumption? I mean, aren't all parties disincentivized? Do you need to know?
Yeah, so in the mechanism, we can only disincentivize the slower parties or whoever is not faster than other people from collusion. But if you have suppose you are the party who have absolute network advantage over other people, then you are actually incentivized to collude because you can always submit reports first. But because there always exists someone who are not faster than everybody else, then this party is disincentivized from collusion, and that's the only thing we wanted to achieve. Yeah. Okay. So we will be comparing this two according to 5 metrics. The first two are about how many malicious parties they can tolerate without jeopardizing fairness or effectiveness of the scheme, and the fairness hazard, and the applicable access structures, and also the robustness number. So for W0P, because it applies to any access structure, it achieves the best robustness number possible, minus k plus 1. So this is achievable with threshold access structure. And for the second mechanism, its robustness number will be increasing with omega monotonically, given a fixed n and k. But the effectiveness will be decreasing with omega. So there is a trade-off between these two metrics. So overall, W0P, the first mechanism, applies to more general cases, but it has fairness issues. And for W1P, it applies to tasks only, but it achieves the best fairness possible. So this is the comparison. And next we will be showing that task is actually relevant. We connected task to some existing objects. So such as partial standard systems and binary constant weight codes or uniform subsets with restricted intersections. So these are an equivalent. So based on the equivalence, we can bound the size of the task. So remember the A2 we had where we had this triangle shaped access structure? That is the optimal one where we can achieve the maximum size. You cannot construct another 7, 3, 2 tasks with a larger size in terms of number of minimum sets in that access structure. So after having this bound, we can construct optimal size tasks based on the equivalence to other systems, and we can also construct near optimal tasks based on Reed-Solomon codes or algebraic geometry codes. And we also, in the meantime, ensure that we achieve high robustness. And finally, we'll be illustrating how to construct efficient VSS on these task structures. We did this in construction on NK2 tasks only. So if we use the BL transformer, then we can achieve all of n square information rate. But if we do something clever, by first decompositing the access structure into style structures and then using the standard techniques, we will be able to achieve all of n information rate. And then after we have a secret sharing scheme, we can just apply the generic compilers to make it verifiable. So we have a VSS. And this is about how we show the practicality of tasks. And what we have so far is approaches to deter parasitic occlusion under general structures. And the key takeaway here is that by using rationality, we will be able to potentially disincentivize parties from collusion, and by using some adding structure to access structures, we can potentially limit the fairness hazards of those mechanisms so that we don't punish or penalize or affect non-colluding parties. And there will be trade-offs between generality, effectiveness, fairness, and robustness when we do this kind of designs. So this will be about collusion. And do we have any other questions about this? Okay, then we can move on to there are many open problems in this direction as well. And we can move on to the next angle where we look at the opposite. So in collusion problem, we don't want people to collude to reconstruct. But in rational secret sharing or pair reconstruction problem, we want parties to reconstruct, but they don't want to. So how do we motivate them to do this? And so for collusion problem, it's applicable to PIR, DKG, and PC secret sharing with conditional reconstruction. For rational secret sharing, it applies to cases where reconstruction is needed. So like the last step in secret sharing based on PC, where parties are supposed to reconstruct the output. So let's motivate the problem a little bit. So suppose I'm a captain, I wanted to smooth a map among 4 of my crew members. I want them to reassemble the map when they reach the destination. But why would they? I mean, the question is, why do the parties would cooperate when they reach the destination to reconstruct? So suppose here, 3 parties have contributed the map. Then for the remaining party here, not contributing can actually be beneficial if he wants to be the sole party who learns the map. Right. So the problem will be more evident if we consider a specific preference profile. So here, because if parties are just altruistic, then they will definitely share, but what if they're not? So when we consider a specific preference profile proposed by Hoppe and Teague in 2004, then there are 3 elements to it. The first one is that if we have the same outcome about who learned the secret, then everybody has the same utility. And the second, parties would prefer learning to not learning. And finally, when parties do learn, they prefer fewer other people who also learn the secret. So under this set of preference profile, there's an impossibility result for deterministic protocols. So there does not exist a deterministic fair reconstruction with a known bounded number of rounds of interaction among the participants, even under network synchrony. So the intuition is similar to something we discussed earlier. So if we have a known bounded number of rounds, then that means we can do backward induction. And if in the final round, we prefer fewer other people who learn the secret, then we will not be sharing with other people if they have already shared. And in all other cases, we don't care. We are indifferent between sharing and not sharing. Only when other people have shared, then I don't want to share, because that makes me the only person who learns, and this satisfies the preference profile 3, and it will increase my utility. So the intuition here is that in backward induction, not sharing dominates sharing. And the intrinsic reason is that the last party to share will be able to learn the secret with other people's provided information. So if we wanted to work around to circumvent this impossibility, we will need to cut this out. We will need to remove this intrinsic cause. So first, we assume we have network synchrony. And second, we will make sure the parties will move simultaneously. And finally, we will randomize the reconstruction termination with fixed secrets. So to be more specific, in each round, the dealer or some helper will be sharing the true secret with certain probability, which is tied to the utility functions of the parties. And the parties will be aborting if someone does not share in the previous round. So because a party would prefer learning to not learning, then they don't want to not sending a share and causing other people to abort and causing themselves not be able to learn the secret. So this probability has to be set according to this utility function. And how do we make sure the parties move simultaneously? Well, we either use simultaneous broadcast or time primitives like time delay incursion or hash time lock puzzles. So whenever a party is in the next round, their message from the previous round is already revealed, so they can't do anything to change it. So that's the spirit of using time primitives to do this. And the recent work based on this workaround is from 2017. And they assumed verifiable random functions, authenticated secret sharing, synchronous broadcast, and they achieved a protocol with round complexity approximately 3, and they can tolerate almost half of the parties being in a coalition, but they cannot tolerate malicious parties. They cannot tolerate a single malicious party. So, but this protocol doesn't have set information resistance. So what do I mean? in the probabilistic termination, the parties will be sharing because they can't tell if a round is a actual round with an actual superior node. So that's why they proceed to the next round and send messages. But only if they can tell through some set information prior existing knowledge, then they can terminate earlier than that. Just by gathering information from other people, they can tell if it's a real round, then they will not share the information. So this protocol is vulnerable to this kind of attack. And in this work, what we will be doing is to devise a deterministic RSS protocol. And we only assume network synchrony, but we do assume a new set of preference profiles. So we will formally define this, and we have a deterministic RSS construction. And just to list some of the benefits of this protocol, it applies to general access structures. It terminates in at most 2 rounds. It doesn't use any heavy cryptographic machinery. It doesn't require knowledge of the exact utility functions because we don't require probabilistic termination. And we allow arbitrary set information. The protocol has essentially no communication overhead, and we can tolerate collusion of size up to n, and the malicious parties not covering all the access groups. So this is the robustness number that we mentioned earlier. These two will be equivalent. And to give intuition, we will look at the toy example. Suppose we have two access groups, and the 4 parties on the left side will be able to reconstruct, and the 4 parties on the right hand side will also be able to reconstruct. So there exists this universal party. So what this universal party will be able to do is to threaten people. So if you don't give me your shares first, then I will never share with you, and I will just collude with the other group. So this is the computation part. So if this universal party is actually super patient, so it will be waiting until other people cave in, then this will be credible, and other people will be sharing as early as they can, and this universal party can actually fulfill the threat. If this universal party is actually not patient, and instead they are super impatient, then they are effectively like a normal party. So this threat won't be discarded by the people. So here, a patient person would consider $1 tomorrow almost the same as $1 today, but they don't want to. They can wait, but for impatient people, they don't want to wait. Yeah. So this is the intuition behind the rational secret sharing protocol that we will all be discussing. And for our preference profile, we considered that in practice, information can be time sensitive, and there can be competition among reconstruction groups. So we changed the first preference profile to that when we have the same outcome about who learned the secret and when, we have the same utility for everybody. And the parties will prefer to learning the secret earlier than later. They not necessarily strictly prefer this, but we assume they prefer learning earlier than later. The second utility profile, utility function stays the same. The third one is that when parties learn, they prefer fewer other people who learn before them. So as long as fewer people learn before them, they don't care how many people learn after them. Okay, so for example, for example, for U1 star the watch engine, this would apply to treasure hunt type of games. Because if I learn the secret, I know where the treasure is hidden, then I can just go get it. And I don't mind letting other people know about the map afterwards because I already got the treasure. And for the third utility function here, it's applicable to like stock markets where other people buying the same stock after you will potentially increase the bid prices and benefit you, so you can sell higher. So this type of preference profile apply to the cases where the secrets generate time-sensitive returns and can be capitalized fast. And or when parties benefit from other people taking a certain predictable action after learning the secret, like buying stocks after you. And finally, it applies to cases where accomplishing computation tasks faster facilitates the progress. So next we will be doing the analysis one by one. We divided the potential cases into three. The first case is that when we have a non-singleton access structure and we have non-overlapping groups. So each group are in it for themselves, so they were competing with each other. So in the final round T, we have an equilibrium that either all the parties share or at least two parties do not share. So in one case, everybody learns, in another case, nobody learns. And then in the second to last round, sharing will provide higher utility because parties prefer to learn the secret than not. If they are going to learn, prefer to also learn earlier than later. And then when we reason backward to the first round, all the parties will be incentivized to share in the first round. So overall, in the final round, the second equilibrium, where at least two parties do not share, will be eliminated when we do backward reasoning, and only the sharing equilibrium will be preserved. So does the intuition here make sense? Yeah, so this is the purely competitive case where the parties don't have any overlapping, where the groups have no overlapping parties and they're just competing with other people to learn faster, because the third utility function is that they prefer not to have other people learning before them. Yeah, so then the scheme is very simple. Everybody just send each other the shares in the first round. The second case is when we have a non-singleton access structure and we have a universal party. And as we mentioned in the toy example, the universal party can just claim to only send shares to the parties who have sent shares to them. And this is only credible if the universal party is sufficiently patient and other people prefer learning the secret earlier, even if they have to let one party, this universal party, learn before them. So if this is a credible claim, then the common normal parties will be sending the shares to the universal party in the first round to learn earlier. And if it's not credible, then it's similar to case A we had, and they will also send to each other the shares in the first round. So when we have credible claims, then we have a 2-round protocol, and we have non-credible claims, we have a 1-round protocol. So when we have multiple universal parties, and then these credible universal parties will be sharing with each other in round 1, and the common parties will behave as before. So we can simply view the credible universal parties as if they are one party. So if they can make credible claims, then the common parties will follow to send them shares in the first round. But if they're not credible, then everybody has to send each other shares in the first round. So this is the scheme for this case, and it takes at most 2 rounds. And finally, we have a non-singleton access structure. We have overlapping groups, and there's no universal party. And this will depend on whether we have locally universal parties. So we can break the access structure into substructures so that we can potentially find local universal parties, and the locally universal parties can make claims as the universal parties in case B. So if those threads or claims are credible, then the common parties will be sending their shares to them first. But if they're not credible, then everybody shares in the first round. Yeah, so this is the basic intuition for this case. And we do handle collusions up to size n. And for malicious parties, we can tolerate n-1 malicious parties, where m is the robustness number or the minimum vertex cover for the hypergraph constructed from the access structure. We cannot tolerate universal malicious parties. So if there is an access structure with universal parties, then we cannot tolerate even one malicious party. So, but we do note that this does not exist in commonly used access structures like a threshold structure. And finally, we have left out one case where we have a singleton access structure. Then we needed to change the utility profiles to have or desire or to make sure the current analysis goes through. That is to assume parties strictly prefer learning the secrets earlier. So because there's only one group, there's no competition, so we needed to enforce that they prefer learning earlier, then that's why they will be sharing in the first round. So in summary, we wanted to ask the question about like what if fewer parties are honest, and then there are two tasks we needed to do. The first task is to motivate desired actions. So in restaurant execution, we only needed to actually motivate one single action, signatures, and this is still non-trivial. And this is because we're considering potentially undesirable preference profiles, let's say that parties prefer others not to learn. So if we are considering even general protocols, then motivating them to do more actions, then it's going to be even more non-trivial because we have way more undesirable preference profiles to consider. And the second thing we need to do is to disincentivize undesired actions. So in this case, if this action is kind of detectable, then we can adopt accountability techniques and then add simple penalty mechanisms. But if it's theoretically detectable, like the collusion problem we were discussing, then we can try to design more intricate penalty mechanisms. But if it is actually undetectable, then it seems like a dire cause to try to disincentivize this undetectable actions. If those undetectable actions can cause security breaches, then there seems to be nothing that we can do. And finally, how do we compose rational protocols with different preference profiles? Because apparently we are considering very different preferences when we design different protocols. So I will leave with these questions, and these are the references, and thank you for your time.